So let's talk about some of this trig in terms of its applications, ways we can start using this trig. You'd probably call these word problems. The first one we're going to do is very basic. How tall is that building over there? You're, I don't know, 6 feet tall, and you stand 40 feet from it. The angle of elevation to the top of the building is 31 degrees. Whenever you do word problems, I've got a few pieces of advice. One is draw a picture. I was the kid in school that I never drew the picture because I never thought that I needed to. And then once I started drawing the pictures, I realized how helpful it was. If you can make it to scale, as to scale as possible, you should, but it's not that big a deal. 2 is find everything, even stuff you don't think you need. Find every angle, find every side, draw extra heights, or draw altitudes, or anything extra that you can find. Drop a right angle from somewhere, cut an angle in half, whatever it may be, whatever you can work with, just try and do it. So we are going to draw a quick little building here. I'm going to try and keep my colors real pretty. So this building is going to be rectangular and tall and thin. You and I are also tall and thin. Congratulations, we've done it. And it says we are standing 40 feet from the base. So this distance here is 40 feet. And I guess we're looking down with the way that our neck is angled. It says the angle of elevation to the top of the building is 31 degrees. Well, angle of elevation means here's horizontal. Angle of elevation is the way up. This is the angle of elevation. And angle of depression is the way down. If you're looking down from horizontal, it's called an angle of depression. If you're looking up from horizontal, it's called an angle of elevation. We're doing the elevation, so we're looking up. And to be 31 degrees, well, the way that I have it drawn right now, this angle here is definitely not 31 degrees. So I'm going to pull all this out. It doesn't actually matter, but I figured I might as well try to make this thing somewhat accurate. So this distance here is 40 feet. This angle from my eye to the top of the building, this angle here is 31 degrees. That looks a little better. We are trying to find this height, h. This is a very simple, basic trig problem. We can start by just looking at this triangle. This is 40. This is a right angle. It doesn't actually matter if the building is built to a right angle. The building could have some sort of a slant to it or something, or it could be architecturally cool. So suppose we had like the Leaning Tower of Pisa. We can still find this height. It's always just the height from perpendicular. So the angle of the building doesn't actually matter. I just want to find the total height. Well, the first height I'm going to find is this red height here, the height of this triangle. From this angle theta right here, this is the opposite, this is the adjacent. So the tangent of 31 is going to be opposite over adjacent. Multiply both sides by 40. And you get that red height, h. 40 times the tangent of 31 is 24. We also said we were 6 feet tall, so this space here is going to be, we'll just call it 6 feet. You can maybe worry about like how your eyes, if you're measuring from where you're looking, your eyes aren't exactly 6 feet tall. Whatever, the point is the building's 30 feet. 24 plus 6. Nice, basic, simple. Let's get slightly more complicated. Directions are kind of a big deal with trig. A lot of the trig that was originally accomplished was through ships and sailing and navigation and maps and cartography and all that good stuff. So here is a compass with north, south, east, and west. And it says ship A is sailing 12 degrees north of west. Well, that means that from west I go 12 degrees north. So this is ship A. It's sailing in this direction. I don't know how far it's going. I just know it's going in that direction because this right here is 12 degrees north of west. Ship B is sailing 15 degrees north of east. Although I think I wanted that to be east of north. Just to show how it can be different. East of north would mean from north we went east 33 degrees. No, 15 degrees. So this angle here is 15 degrees. The question then becomes, how far apart are the two ships? Well, for one thing, we aren't totally sure how far they've gone yet. Like if ship A is going 40 miles per hour and they're sailing for 4 hours total, then ship A has gone 160 miles. Ship B is going at 33 miles an hour for 4 hours total, so that's 132 miles. But because they're not sailing directly away from each other or directly towards each other, we can't just add or subtract to get the distance they are from each other. We have to find the length of this triangle here, or I guess that side of that triangle. Well, to do that, we'll need to know some other angle in here. We've got to find this angle here. And I feel like at this point, this might already be kind of confusing just looking at all that. So I'm going to redraw this triangle. Where this is 160, and this is 132, and those lengths are already off, but I don't really care that much. I knew that this right here was 12 degrees, and I know that this right here is 15 degrees. So the question becomes, what is this side here? Well, I can work with this angle right here. I know this total angle there is 90. So if I take off this little 12 right here, that's 78 degrees. So this little filled in part right here is 78 degrees. Then we tack on this 15 right over here. I don't know why I'm using this green. I should pick something a little bit darker. This part here was 78. This part here was 15. So altogether, that's 93 degrees. Because we have a side angle side triangle, I'm going to use the law of cosines. If we had a regular right triangle, I could use sine, cosine, or tangent. If we had a side angle pair, I could use law of sines, but we don't, so I'm going to use the law of cosines, which is c squared equals a squared plus b squared minus 2ab times the cosine of c. I'm going to call this angle c and this side c. I have to use this as angle c, because it's the only angle that I actually know. So I don't know my C side, but I know that A is going to be 160, B is going to be 132. I don't know why I keep putting a degree up there. It's going to be 132 squared. And then it's minus 2 times 160 times 132 times the cosine of 93. And I'm going to calculate this. (160 squared plus 132 squared plus, nope, minus 2 times 160 times 132 times the cosine of 93. Of course, make sure your calculator is in degrees and not radians. That gets you that big old honkin' distance. But remember, that's c squared. C squared equals that number, 45,234. So c equals the square root of that. The square root of my previous answer is 212. A distance of 212 miles is very reasonable given these lengths in this triangle. I mean, it could be at most 292 if they're sailing directly away from each other. It could be at the very least 28 if they were sailing in the same direction, starting at the same point. Because they're going at some different angles, it's 212 feet. I'd like to take this time to let you know there's something called minutes and seconds of a degree, which might be coming up on quizzes or tests that we have if you're in my class. 1 minute is 1/60th of a degree. So 1 minute in terms of angle measure, there's an angle measure called a minute. A minute is 1/60th of a degree, which is clearly what that says. And then 1 second is 1/60th of a minute. So 1 second is 1/60th of a minute, which makes it 1/3600th of a degree. So you can break down degrees into really, really small pieces, which is helpful if you have a very, very big circle you're working with, like, you know, the globe of planet Earth. Okay, here's a new problem. 2 forestry lookout towers are 482 miles apart. So I'll call this tower A, and I'll call this tower B, and this distance here is 482 miles. They're probably on top of some mountains somewhere. The angle formed from the fire, they see a fire somewhere, way out here, we'll say. This is my big, scary fire. The angle formed from a tower from tower A, from the fire to tower A to tower B is 71 degrees. That means this angle here is 71 degrees from the fire to tower A to tower B. So I totally wrote that backwards. This angle here is 71 degrees. Fire to tower A to tower B. Then it says the angle formed from the fire to tower B to tower A is 35 degrees. How far is the fire from each tower? This is another scenario where I don't have a right triangle, so I can't just use plain old sine, cosine, tangent. You'll find most things work out that way, at least initially. But I know that if this is 71 and this is 35, I can find this angle over here. And always just find whatever you can. You know, I wasn't asked to find that angle, but if I can find that angle, which I can, I might as well, and it makes everything a little bit easier. Well, 71 plus 35 is 106. Since everything has to add up to 180, this angle here is 74 degrees. This angle here is 74 degrees. Now I have an angle side pair. This angle and this side pair, so I can do the law of sines. The sine of 74 over 482 is equal to, let's do the sine of A, over, we'll call this side A. Well, we know that sine of A, that angle A, is 71. So I solve this for A. I cross multiply and divide. So A is going to equal 482 times the sine of 71 over the sine of 74. Make sure to close parentheses correctly. Order of operations, 474 feet. Or miles. So this is 482, this is 471. We can find this one in the exact same fashion. We don't want to use Pythag here because we don't have a right triangle. So I'll find side B by doing the sine of 74 over 482. Equals the sine of 35 over side B, which is this side now. It's the exact same process as the last one. And we get sine 35 times 482. Is that? Nope. Sine 35 close parentheses times 482 is that. Divide that by sine 74. 287. With that info, either of these towers could call the fire department and say, I know where this fire is, go put it out, and give coordinates and give locations and distances and everything. based only on already knowing this distance and the two towers being able to measure this distance, or sorry, those angles. And typically they wouldn't actually do it in terms of the angles from each other. They would do it from just the angles they're doing north, south, east, west. So they would say, from me, the angle was this, and from you, the angle was this, and they have a little bit more work to do. And I think we'll do a problem like that in class. But the process principle is still the same. This is the type of problem that I think is super cool. Okay? There's a mountain over there, and we're going to find the height of it. I think it's so cool that you can find heights of things without climbing them, and without being close to them, and without even like knowing how far you are from the thing. So if you think about like some, mountain out here, and we'll make this a nice pretty little snow-capped mountain because we're going to assume it's pretty tall and there's some snow there, maybe some snow there or something. We want to find how tall it is while we, our purple selves, are standing way out here. So what we do is, from the ground, at our current location, the angle of elevation from the ground to the top of the mountain is 14 degrees. This angle here is 14 degrees. Then we take we travel 500 feet closer. So this distance here is 500. Then we measure this angle. And this angle here is 15.3 degrees. So it didn't increase by much, which makes sense because the object we're talking about is really far away, probably. And we know now it's pretty far away because of those measurements we just took. We are trying to find this height right here. It doesn't matter that there's some mountain in the way over here, or that this looks like a peak and here's another peak. We could find this peak if we wanted to. The point is, with just these two angle measurements and this distance traveled, we can find the height of this mountain. And at this point, you can keep that triangle there, but I often like to draw another one that's a little bit cleaner. So I'm going to call this 14 degrees. This is 15.3 degrees. This is 500 feet. And we are trying to find height h. I guess I'll draw it from here. Height h. And that's actually probably even too small for me to work with. So maybe I'll just go back to the original. So, like I said before, I'm going to find everything that I can. I just want to find every angle, every side. I might find some heights of other things. I know that if this is 14 degrees, well really, I'll start here. If this is 15.3 degrees, these two things have to add up to 180. So the green thing I just drew, that I'll now make blue because the green's too faint, I think. The green thing I just drew, which is now blue, this angle here has to be 180 minus 15.3. 164.7. And if that's 164.7 and we already have a 14, we can find this little angle up here. It works out to be, I believe, 1.3. 180 minus 164.7 minus 14. Well, I'm going to add these two up first. I'm doing this in kind of a weird order. This becomes 178.7. So 180 minus 178.7, this is 1.3 degrees up here. If you're wondering how I knew it was 1.3 in advance, there's this theorem you probably learned in geometry, this little, theorem's not the right term, but this angle is always going to be the difference of these two. So one was 14, one was 15.3, so this little guy up here is 1.3. Now I can find this length here or this length here. I don't think I need both. I just need one of them. So I'm going to find one of them. I'll do the one on the outside because it gives me more room to write, quite frankly. That's why I'll pick that one. So I'm going to find the length of x. So I'm going to be looking at this triangle here. And doing that thing that I just did where you highlight the triangle that you're dealing with, and maybe even you pull it down and you work with it down here, can be really clarifying of what you're doing. So here's 14, here's 1.3, Here's 164.7. This was 500. I'm going to find x. Well, now this is a law of sines. I can do the sine of 164.7 over x with this angle side pair, and I'll do this angle side pair, equals the sine of 1.3, that's a very bad 3, 1.3 over 500. Solve that for x. So sine of 164.7 times 500 divided by the sine of 1.3 gets me 5815. This whole length here is 5,815 feet. A little over a mile. I'm going to go back up here. This is now 5,815 feet. Now my goal was still to find this height here. But I can do that now if I look at this triangle. That yellow triangle is a right triangle. And it's got 14 degrees here, 58.15 here, and I'm trying to find this height here. Well, based off this angle, this is the opposite and this is the hypotenuse. So I'm going to do sine. With that triangle, I can do the sine of 14 degrees equals h over 58.15. Let's just go ahead and make all that darker. Solve that for h. 5,815 times the sine of 14 equals h. $1,406. This didn't end up being super high. You know, it's like maybe a quick little hill, and I maybe should have made it snow-capped, or maybe we're already at a very high elevation in the first place. But what I still think is super, super cool is the fact that we can find this height without climbing the mountain. And in fact, we can find that height without walking up to the mountain. From wherever we are, we can just make two angle measurements and measure one distance and find the height of something. And in fact, now if we really wanted to, we could also find this distance and see how far we are horizontally from the mountaintop. Like here, we could see how far we were in a straight line from the mountaintop, but we could also just see anything we want to find just based on a couple of these quick measurements. So I hope you're getting the idea of draw a picture, make it to scale if you can, more or less. Find everything you can find, angles and sides, draw things that maybe you don't know if you need, and eventually piece it all together. If you can make clear work, give yourself enough space, and troubleshoot as you go, check your work, see if your answers make sense, a lot of these problems should be very doable. We did it. We got through another math video. Thanks for watching. Here I'm going to play with the perspective on these shapes while I talk to you. Please subscribe to the videos, like the videos. Okay, let's start this thing over. You did it. You got through the video. Thanks for watching. I'm going to play with the perspective of these shapes, which is always pointing towards that center while I talk to you about things. Please subscribe to the video, the channel really. Please like it if you found it helpful. If you want to share it with friends and say, hey, this guy's not the worst, that's an option too. You can always take your video quiz if you're in my class. And comment down below. See you next time.